Okay, so this video is about permutations and combinations, and really our objective here in this video is our learning objective is to solve counting problems, we're still counting, using this permutation and combination concept, which you'll learn shortly. You'll see that it's just an extension of some of the things we've been doing with the multiplication principle. The idea with permutations and combinations is going to give us a shortcut way of finding the number of possibilities for choosing a subset of a group. So for example, if I had 6 things over here and I wanted to figure out how many ways could I choose 3 of them, this is the kind of math we're going to use to help do that. Before we move on to permutations and combinations, we have to talk about ways we can choose. Sometimes order is going to be important when we choose things. For example, for those of you familiar with baseball, say we have a 15-person baseball team. That's supposed to be a 15 over here. A 15-person baseball team, and we need to pick a lineup which is going to have 9 people. Well, here it's pretty clear that order is going to be important. If I pick person A in the first position here, and then for a different lineup, position B, when I choose these 9 people, the order is going to be important because I care what order they're in. So that's a situation where order is important. But sometimes when we choose, order is going to not be important. For example, when we do pods in class, if we have 19 students in the class and I want to pick 4 of you for a pod, I don't really care what order I pick you in. If I happen to pick student A, B, C, and D in that order, I'll get the same pod if I pick the students in D, C, B, A order. So these are going to be considered the same because it's a grouping of people. So this is a situation where order is not important. And you'll see that this is going to be the key distinction between permutations and combinations, this idea of order being important or order not being important. So to introduce this concept further, let's just pick a familiar problem from multiplication principles. So this first problem up here is how many ways can you select a president, vice president, and treasurer from a club with 12 members? Hopefully you all know how to tackle this problem now. We can see we have 3 different actions we have to take. We have to pick a president, a vice president, and a treasurer. And the ways that we can do that here, order is going to be important because when we pick the first person, they're going to be the president. That's different than picking that person to be the vice president. So when we pick this first person, there's 12 possibilities for the president. Once we've picked one of them, there's 11 possibilities left for the vice president. Once we've picked a vice president, there's going to be 10 left, for the treasurer. And when we multiply those out, we get 1,320. So this is a situation where, again, order is going to be important. I'm going to abbreviate important there. Now let's take a peek at this problem down here. How many ways can you select a 3-person committee from a club with 12 members? So we're dealing with the same club, 12 members, but now we're trying to pick a 3-person committee. Here order is not going to be important. It's almost like a pod situation. But what we can do though is start with what we did up on top. We have the 1,320 ways to pick 3 people where order is important. But think about it, when we pick 3 people, there's going to be a bunch of other groupings that are the same. Well, how many are there? So let's just pick, if we've had A, B, and C, if those happen to be the people we picked for the president, vice president, and treasurer, how many other orderings of that group are going to be the same group? Well, here we can use our same multiplication principle concept. If I want to reorder these 3 people, there's going to be 3 that could have been in the first position, A, B, or C. Once I've picked one of those, it's 2 left, and then there's 1 remaining. So there's really, in this particular problem, there's 6 different ways that A, B, and C will have shown up in this problem. It would have been ABC, ACB, BAC, CAB, CBA, and then there's one other one. So the way we can solve this problem then is really just to start with what we did with on the top, but now we're going to divide it by kind of undoing the ordering that we found with these ABCs. So for essentially every group of 3 that we could have picked, there's going to be 6 possibilities of how they would have been ordered. And so we're going to divide through by that factor here to get 220. So there's 220 ways we could have selected a 3-person committee from a club with 12 members. And not coincidentally, that is 3 factorial. What we've just done up here turns out to be a permutation. We've chosen a group of 3 people out of 12 where order was important. And what we've done down here is a combination. We've chosen here a group of 3 people from 12, but order was not important. So that's the basic gist between the difference between permutation and combination. Now I'm going to move on, and I just want to give you the formulas for these, and then once you practice with them, you'll see kind of why they work. So for permutations, let's abbreviate that with P. There's actually a notation we're going to use. We're going to use N, P, a big P, and a little r. N in this case is always going to be the number of items in the group. And then the r is going to be the number of items being chosen. Okay, so that's how we're going to call this NPR. The formula for that's going to, it turns out this is where factorials are going to come in. That's why I said we needed to be good at them. It's going to be n factorial, and we're going to divide through by n minus r factorial. So for example, with the 12-person committee we had just done, we would have had 12p3. We're choosing 3 people from a group of 12. P is a permutation where order is important, and we could have solved that problem quickly by just writing 12 factorial divided by 9 factorial. Oops, sorry, 9 factorial, where 9 is 12 minus 3. And then kind of like the problems we worked today in class, that's equal to 12 times 11 times 10 times 9 factorial over 9 factorial. Those cancel, and you get the 12 times 11 times 10. The combination side of things, not surprisingly, is going to have a similar notation. NCR now, meaning combinations, the number of ways of choosing R things out of a group of N when order is not important. That's going to start off looking very similar to the permutation formula, just like we did in the prior problem. It's identical, but then we just have to divide through by the potential orderings of R that would have been counted up here. So we're just going to do another division here, divided by r factorial. And that r factorial really undoes the ordering when we say order is not important. So for example here, when we did 12c3, that was the problem we had just done. We would have done 12 factorial divided by 9 factorial times 3 factorial. And when we simplified that out, we would have gotten to the 220 answer. I'm going to go ahead and write 1320 up here. Okay, so these are the main formulas you want to get out of this. They're pretty simple to remember, and N and R has the same meaning in both situations. Okay, so now let's just do 3 examples, and then hopefully you'll be good to go in understanding at least the basics of permutations. These problems do get complicated, but these examples, hopefully, they will not be complicated. Okay, so our first example is a company advertises 2 job openings, one for an accountant and one for a financial analyst. If 10 people apply who are qualified for either position, in how many ways can the openings be filled? Well, so what we have to think about here is we're choosing, how many people are we choosing? Well, we're choosing 2 people, and where are we choosing them from? Well, we're choosing them from a group of 10. So it should be clear that we're going to have 10 something. I'm going to leave that blank for now, 2. So now the question is, when we're choosing these 2 people, do we care about the order or do we not care about the order? Well, here we have a job, it's an accountant and a financial analyst. So even though they're both qualified, the accountant and then the financial analyst are going to be different jobs. So this is a situation where order is going to be important. So really what we're doing is permuting them. So we're choosing a group of 2 people out of a group of 10 where order is important. And then from our formula from the prior page, we know that that's 10 factorial divided by 10 minus 2 factorial, which is 10 factorial over 8 factorial, which equals 10 times 9, because once I write this out, the 8 factorials will cancel. Now this could have been done directly by the multiplication principle, but again, it's helpful to use this same notation for permutations when the problems get more complicated. And then multiply that out to get 90, and we're done. There's 90 ways that 10 people can apply to fill 2 job openings where the jobs themselves are distinct. Example 2 here, we have a company advertises 2 job openings for computer programmers, but in this situation, both have the same salary and job description. And how many ways can the openings be filled if 10 people apply? Well, in this situation, these 2 jobs are indistinguishable. There's not really an order that's important. All we care about is what 2 people are going to come work as computer programmers. So this is a situation where we're going to, group of 10, we're choosing 2. In this case, it's going to be a combination because order is not important. And then we could go ahead and use our formula for this. It's going to be 10, 8 factorial divided by 2 factorial. It is the case that whenever you do a combination, these 2 factors down here will always add up to the 10 on top by construction. So that's a good way to check to see if you've done things right. So 8 plus 2 equals 10. So yep, I did that right. And then we could go ahead and finish this off. That's going to be 10 times 9 times 8 factorial. 8 factorial. And I'm just going to simplify. 2 factorial is 2. These 8 factorials are going to cancel. 2 divided by 10 is 5 times 9 is 45. So this last example is going to have a little bit more complexity to it. Example 3. So we have a class of 10 girls and 15 boys, which means we have 25 total in our class. So the first question here should be pretty straightforward. In how many ways can we choose a group of 4 students for a pod work group? So like we do on all these problems, we've got to think about how many people are we choosing from? Well, we have 25. How many people are we choosing out of that group? Well, we're choosing 4. And now, is order important or not important? Well, this is a work group. Everyone's just going to be sitting at the table. It doesn't matter what order we select them. So this will be the combination variety since order is not important. If we were going to just write that out in factorials, that 25, the total appears on top. And then we're going to have 21 factorial on the bottom times 4 factorial. And again, our check with combinations is that 21 plus 4 should equal that 25. And turns out that that number will be 12,650. You can actually do this on a calculator, which I'll show you in class. In how many ways, so part B now is how many ways can we choose a group of 4 students for a pod work group if there has to be 2 girls and 2 boys? Well, this gets a little bit more tricky because now we're not just dealing with a single group of 25 students anymore. We have 2 separate groups, 10 girls and 15 boys. So we have to go back to our trusty multiplication principle and then think about the boys separately from the girls. So here we want 2 girls. I'm actually on this side, 2 girls. Well, how many girls do we have? Well, we have 10 girls, and we're going to choose 2 of them. And again, this is a pod work group, so order is not important. So the way to pick 2 girls out of the group of 10 is 10C2. Now when we think about these the boys, there's 15 boys. We're going to choose 2 of them, 10C2. So we're going to multiply these together because that's the multiplication principle. Number of ways of choosing the boys times the number of ways of choosing the girls. And if we do the math on that, you're going to get 45 times 105 equals 4,725. A good check is this number definitely should be smaller than this number. This is all possible groups. This is just the groups with 2 girls and 2 boys. So like that would be a reasonableness check. If that number turned out to be bigger than that one, clearly we did something wrong somewhere. This last problem then is going to use a couple of our counting principles. In how many ways can you choose a group of 4 students for a pod work group to have at least 1 girl and at least 1 boy? Well, in order to have at least 1 girl and at least 1 boy, remember, when we see that word at least, we want to think about complement principle. So the way I'm going to approach this is find the number of groups that have all girls, find the number of groups that have all boys, and then take them away from the total up here. So the number of groups that have all girls, well, how many girls are there? Well, there's 10. If I choose all girls, means I'm going to take 4 from the group of 10 girls. So this is all girls. Girls. And just to be clear what's going on with the boys, there's 15 boys, but I'm choosing 0 of them. So I'm going to go ahead and write that here just because sometimes it's just helpful to see the pattern. Sometimes that happens. Turns out that's going to just equal 1, so it's not going to matter. And you can see that through the formula. 10C4 would be the number of all girls. And when you punch that into a calculator, you get 210. Now for the boys, well, we have 15 boys. All boys would be 15C4 times, and again, just to be clear what we're doing with the girls, we're choosing 0 of them. So there's 10, but we're choosing 0. That's going to equal 1. So I'm just going to maybe put that in parentheses to show that it's kind of hidden in there. This one's going to be 15C4. Punch that into a calculator. You get 1365. So to finish this off then, the problem would be how many ways can we choose a group of 4 students for a pod to have at least one girl? Well, we're going to start with, this is where we use the complement principle. We're going to start with everything, subtract off the 210, subtract off the 1365, and that's going to give us 11,075 groups here that have at least one girl and at least one boy. So most of them. And that concludes the examples. Just to finish off here, if I click back to our formulas for permutations and combinations, just to review, again, permutations are when order is important. Combinations are for when order is not important. The formulas are related. The only thing that's different between them is this factor down here, the R factorial between the combinations and permutations, and really what that R factorial is doing is undoing the order being important. So that's just a good way to try and remember that instead of just blindly memorizing the formulas.